Hello everybody, so this is the first video associated with chapter 2 of the reinforcement learning course. So the purpose of this chapter is to introduce a first class of reinforcement algorithms in a very simple setting, which is called the K-arm bandit setting. Okay, so in this setting, what happens is that there's a single possible state and states of the nature and a finite possible number of actions. Okay, so having a single state in the problem simplifies the problem, and then we'll go to more complicated models in subsequent chapters. Okay, so this setting that we will study, it's referred to as the K-arm bandit, as just mentioned, and it is covered in chapter 2 from the textbook. So now we will describe a bit more thoroughly that K-arm bandit problem. So why is it called K-arm bandit? Well, it's an analogy to an like arm bandit or slot machine, except that there are multiple arms. So in slot machine, you have one arm that you pull. Well, here you have K possible arms from which you can pull. So this is why we're gonna call it K-arm bandit. Okay, so in that problem, the K-arm bandit problem, you are faced repeatedly with a choice among K possible actions. So you can think of K possible levers, and you're repeatedly faced with the choice of selecting one of the levers at each time step. So every time you choose an action A, okay, A is the lever which you pull, you will receive a reward from drawn randomly from a distribution denoted by FA. So here FA is the distribution associated with the reward when you pull arm A. And furthermore, at every step, every time you pull a lever, we're going to assume that the reward you obtain is independent from the rewards you've received in previous steps. So the distribution FA is assumed to be unknown. So every time you pull a lever, you receive a reward from the distribution associated with that lever, but you assume that you don't know that distribution. Okay, so we don't know before the experience what is the distribution. So we want to pull levers to get information about that distribution. And the objective here will be to maximize reward. So this I'll explain shortly. Furthermore, uh, since the distribution FA is unknown, and we're gonna denote the expectation of the reward from distribution FA by Q star A. So Q star A is the expectation of the distribution FA. Okay, and since FA is unknown for all levers A, Q star A is also unknown. So we don't know what is the expected reward associated with each of the levers. So in that problem, the K-arm bandit problem, we're going to assume that the objective is to maximize the expected total reward you get over capital M actions taken. Okay, so we're going to assume that there are capital M time steps, and on each of these time steps, you pull a lever once and receive a reward associated with the lever you pull. Okay, so every time you take an action, such action selection is called a play. Okay, so in this model, we're going to assume that there are capital M plays. Okay, so you have to pull levers capital M times. So the idea here is that maximizing your expected reward, this should be achieved by concentrating plays on best levers. Okay, so if you pull levers, get information about them, and start figuring out that some levers are giving higher rewards than others, then eventually you'll pull these levers more often because they give more reward. Okay, so to maximize your expected reward, you need to try to find levers which give rewards with the highest expected value. Okay, so This is a theoretical problem, but there are analogous real-life problems associated with this framework. Okay, so for example, I'll give one single example. There are many others, but one possible example is in medicine. Okay, so let's say you have patients and you have a set of patients that are seriously ill, and you have a set of possible treatments that you can give to patients. Okay, so every time you assign one of the treatments to a patient, you can see that as a play, although it's not a game. So, according to our terminology, every time you make an action, so you say, okay, this patient, assign him this medication, then this is a play, and your reward can be quantified as either the survival of or the well-being of your patient. So you typically want to improve as much as possible the condition of your patient, and you want to find treatments which are working the best towards uh, improving the health of your patients. Okay, so if we knew the exact distribution associated with each lever, then solving the K-arm bandit problem would be very easy. Okay, so if you knew what is the expected value of associated with each arm, you'd play all the time the best arm. Okay, so you determine A star, which is the lever which has the highest expected value. So it's the argmax, maximizing argument between 1 and k of the expected value associated with arm A. Okay, so you just pick the lever A star, which is the one which has the highest expected value among all levers, and you will pull that one all the time. Okay, so this is in theory if we knew what is the distribution associated with all levers, but in practice these distributions are unknown. So in practice you cannot have exactly the distribution, but you can have estimates associated with this distribution. Okay, so as time goes by, as there are many plays that are performed, you receive rewards from various levers, and you can use these past rewards to build up estimates of the mean associated with all levers, and then you can use these estimates to try to optimize your strategy and try to get the highest possible expected reward. Okay, so these estimates will be denoted by QTA. So QTA will be the estimate of Q star A just before the teeth play. Okay, so let's say Q32 would be the estimate of the expected value of lever 2 just before the third play. Okay, so in practice what we have, these estimates are known, but these true values are unknown. Okay, so then a bit of terminology will define what's a greedy action. So the greedy action after T1 minus place is selecting the action maximizing QTA at the next play T. Okay, so let's say you've played T minus 1 n times, then you have to select an action for time step T. So what you could do, you could look at your estimated expected rewards for all levers, and then take the lever which has the highest estimated expected reward, and pull that lever. So this is called the greedy action. So the greedy action entails selecting the action which you think performs the best as of your current information you have. Okay, so selecting the greedy action at some given play, it entails exploiting your current knowledge about action values. Okay, so what this means is that if you take the greedy action, you will try to pick up the lever which will give you the highest possible reward for the next play. Okay, so you use your estimates, you exploit your knowledge to try to find for the next play what will give you the best reward. So in reinforcement learning, we will see that often we need to sample or to select the greedy action, but sometimes we will see that we'll need to select other actions than the greedy actions. Okay, so these other actions are called the non-greedy actions. So non-greedy actions are the set of all actions which are not the greedy action. And selecting non-greedy actions entails exploring. Okay, so sometimes if you want to maximize your reward, you need to sample often from the lever which you think is the best. But sometimes also it's good to sample from other levers that even if they don't look the best right now, maybe it's because you have bad estimates or of their means. And if you sample from other levers, this would allow you refining your estimates of the expected value for other levers, and you might discover that the one you thought was the best is not the best, and it's another one which is the best lever. Okay, so exploring entails selecting actions that are non-greedy, so that you don't necessarily think they are the best as of your current information, but this allows you refining your estimates of the value of the other actions. And by value here we mean expected reward. Okay, so we're going to discuss now the exploration versus exploitation dilemma, which is very famous in reinforcement learning. So exploitation means you select your greedy action, the one you think is the best as of now, and then this will entail trying to maximize your reward on the next step. Okay, so one might be wondering, well, should you always take the greedy action and always take the action that seems the best to maximize your expected reward? So the answer we will see is unfortunately no, it's not the case, because sometimes exploring is necessary to maximize your expected rewards on the long run. Okay, so exploring, taking actions that seem suboptimal right now, on the short run, typically that might not be good because you're sampling from rewards which are from levers which provide likely lesser rewards, but it might be beneficial in the long run because it allows you refining your estimates of the expected values of other levers. And if you're able to find a new lever which has a highest value, or a higher value than the one you think is currently optimal, then later on you will be able to sample this new lever very often and then reap some reward. Okay, so exploring is necessary, as said here, because other actions than the one deemed optimal currently, they can be discovered as more effective than the greedy one, which is the one being thought as the best as of now. Okay, so if you discover that another lever is better than you thought and better than the one you currently think is the optimal one, then you can exploit that information subsequently and start sampling from this new lever which you discovered is better. Okay, so exploring is necessary for that, but often exploring yields lower rewards in the short run because you sample from levers which seem to provide a lesser reward. So in reinforcement learning, it's impossible to explore and exploit at the same time. Okay, so either you exploit your knowledge and you sample from the greedy action at some point, or you explore and you sample from the non-greedy action. Okay, so because you can do both at the same time, but you need to do both to achieve good results, you have to have some form of balancing between the two. Okay, you need to sometimes explore, sometimes exploit, and the what is difficult is to try to determine what's the optimal level of exploring versus exploiting to achieve your desired goal, which is to maximize your expected rewards um, over all plays. Okay, because um, as we said, the objective here it's not to maximize your reward over the next single play. It's to maximize your average rewards over all the plays that you'll do. Okay, so long run counts a lot. You're not expected to do good only on the next step, but throughout the overall experiment. Okay, so now we said we consider estimates of expected rewards associated with each lever. How do we form such estimates? Okay, so we need to have estimates of the expected value of rewards. How do we do that? Well, in practice, we can use the sample mean of rewards associated with each lever to form estimates of the mean. Okay, so it's like in your statistics class. X bar is a good estimate. Well, good. It's a suitable estimate of mu. Okay, so if you want to estimate the mean of a distribution from IID samples, then you just take the sample average of this IID sample, and this will estimate your mu, your expected value of the random variable. Okay, so here a bit of terminology. AI denotes the action taken at play I. RI denotes the reward obtained at play I. Then we can use the following formula to form an estimate of the mean after the first t minus 1 play. Okay, so recall that QTA is the estimate of the expected value after t minus 1 play of rewards from lever A. Okay, so this can be formed by simply averaging all rewards you've obtained from lever A in the past. Okay, so let's say you've done t minus 1 plays, then you can sum all rewards here. So this is the sum across all t minus 1 first plays of the rewards. And here this is an indicator, which is one if the reward was sampled, was obtained from lever A, and 0 otherwise. Okay, so here you sum all the rewards obtained from lever A, and here at the denominator, the sum of these indicators simply represents the number of times lever A was sampled. Okay, so this is simply averaging all rewards obtained when the reward was drawn from lever A. Okay, so this formula makes sense only if you've sampled at least once from lever A. And if you've never sampled from lever A, then you can set QTA is equal to 0. Okay, so if you have no clue what the average is, maybe you can put 0 as an initial estimate, which might be refined later on. Okay, so what are the properties of these estimates? Well, from the law of large number, I think most of you know that this estimator is consistent. Okay, it will converge to the true expectation. So our average reward from lever A will converge to the true expected value as the number of times lever A is sampled tends to infinity. Okay, so this is a result in probability called the law of large numbers. So So if n tends to infinity, then x bar n tends to mu, meaning that the sample average will converge to the expected value of the each variable in the sample. Okay, so because of that, our as we play the various levers, as the number of times one lever converges to infinity, as the number of time one lever is played often and often, and the number of times converges to infinity, then the estimate of the expected value will converge to the true expected value for this lever. Okay, so here we propose sample averaging of rewards to estimate the expected value for some lever. There might be other ways to do so, but for now we'll stick with this one. Okay, later on we'll discuss other schemes to estimate the expected value associated with some lever. Okay, so now as we mentioned, we formed estimates of the expected value of rewards associated with each levers. Then we have to determine how will we use these estimates to come up with actions, okay, to decide which lever we will sample from at each time step. Okay, so the simplest rule we could think of is to pick the greedy action all the time. Okay, so at time t, the action we're going to select is the one across all levers which maximizes the estimated expected value you will receive. Okay, so as we mentioned, the problem with that is that you fully exploit your knowledge, but you never explore. What's going to be the problem with that? It might be that the optimal action might never be discovered if you do that. Okay, so let's explain that. Okay, so let's say you have multiple levers, and let's call it lever number 1. Lever number 1 is optimal and all others are not. Okay, so if you, let's say at the beginning you sample from some levers, let's say you were very unlucky with lever 1 and you receive rewards which were extremely low. Okay, your estimate of the expected value for lever 1 will be very low because you were unlucky. So if you're always greedy, then you might never sample again from lever 1 because it seemed bad at the onset. So maybe your current estimates of the expected value of all levers will be higher than this one. You'll never sample again from lever 1, and therefore you'll never eventually know that it is the optimal one. Okay, so its estimate, because you don't sample again from that lever, it might remain low for the rest of time. It will not converge to its true value because you don't sample again from that lever, and you will never realize this is the optimal action. Okay, so for that reason, behaving in a fully greedy manner is not satisfactory in reinforcement learning. So you need to have some form of exploration to ensure that your estimates associated with the various actions are refined through times. Otherwise, you might simply miss the optimal action. So another approach that is very famous in reinforcement learning is called the epsilon-greedy approach. So in this approach, every time you have to sample or determine an action, you do the following. Okay, so you will pick with probability 1 minus epsilon the greedy action, and otherwise with probability epsilon, you will sample a non-greedy action uniformly among all possible actions. Okay, so here okay, just a quick note. So I said here non-greedy actions are the one suboptimal, but here just a quick detail. In the epsilon greedy approach, with your epsilon probability, you sample uniformly from all actions, maybe even from the greedy one. Okay, so here the second point here includes both the non-greedy and greedy actions. Okay, so let's repeat that. Every time you have an action to make, it's as if you flipped a biased coin toss with a probability epsilon of being head and 1 minus epsilon to be tail. So if you get tail, then you sample the greedy action. If you get head, then you sample randomly from all actions and you take that action. Okay, so the first case is exploiting your knowledge, taking the greedy action. The second case entails exploring because you might select actions which are suboptimal. Okay, furthermore, this epsilon probability, well, the selection of the greedy or non-greedy action will be assumed to be independent in all steps. Okay, so it's not because you've taken the greedy action in the past step that you'll have more chance of taking the greedy action in the next step. No, we're going to assume that being greedy or non-greedy is independent in all steps. So with this family of approaches, so if let's say epsilon is small, then with very high probability we exploit our knowledge. Okay, because this, if epsilon is small, this 1 minus epsilon will be close to 1. So in that case, most of the time you will be greedy and exploit your knowledge, select the best, what seems to be the best action. But with probability epsilon, a small probability, then you will explore, you will try new actions, okay, by sampling a random one. So for that reason, the higher epsilon is, the most frequent exploration is. Okay, so if epsilon is very small, you'll almost never explore. If epsilon is large, then you'll explore quite often. So what are properties associated with these methods for selecting actions? Well, if you do have an epsilon greedy approach in our k-arm bandit problem, this will ensure that as t tends to infinity, okay, so what's t here? T is the current time step. So t tends to infinity implies that m must also be infinity, so you have an infinite number of plays in total. But here, when t goes to infinity, as time goes by, you're forced to sample infinitely often from each lever. And because you sample infinitely often from each lever as time goes by, then the estimate associated with each possible action will converge to the true expected value for each action A. Okay, so by having an epsilon greedy approach, because you're forced to sample from the various levers infinitely often, then for each levers A, their estimate of the mean will converge to the true estimate. Okay, so because you'll have a convergence to the true estimate, eventually the the greedy action will become the optimal one, and in that case, eventually you'll always select the best action with probability at least 1 minus epsilon. Okay, I say at least because if you explore, you can still get the optimal action. So here it's written with probability 1 minus epsilon, but it should be even greater than that. So it should be slightly greater than 1 minus epsilon. Okay, so I'll just fix that part here later on. Okay, so here these are asymptotic guarantees. So they guarantee that asymptotically, as time goes to infinity, you'll eventually sample very often from your optimal action. But this does not tell us how is the performance associated with the epsilon greedy approach for finite samples. Okay, so if you have a finite number of plays, then your estimates will not perfectly converge. So how will this strategy work in practice? So to answer this question, we will perform a numerical experiment referred to as the k-arm testbed in the textbook, which will be described right now. Okay, so this k-arm testbed is meant to evaluate the performance of the epsilon greedy approach under finite samples. Okay, so in this large experiment, we will have, let's say, sub-experiments where each sub-experiment is repeated 2,000 times. Okay, so the k-arm testbed entails repeating 2,000 times the following. Okay, so every repetition is called a run. Okay, so we're gonna take k is equal 10. So we're gonna assume that we have 10 levers, and then on each run we have we're assumed to have 1,000 plays. So capital M is equal to 1,000, and we have 1,000 plays of the K-arm bandit setting. Okay, so for one given run, we have 1,000 actions to decide sequentially. Okay, so play one, you pull a lever, you receive a reward. Play two, you pull another lever, you receive a reward, and you do that 1,000 times. Okay, so now what are the distributions of rewards for the various levers in our experiment? We're going to assume the following. So for every run, okay, for each run, at the beginning of the run, the average reward will be sampled randomly for all levers. Okay, so the average will be constant through the run, but sampled randomly at the beginning of the run. Okay, so for each lever A, we're going to assume that the mean reward are simulated as IID normal 0, 1. So for each lever, the expected value we're going to assume is simulated randomly from a normal 0, 1. And then furthermore, once we've identified the mean for all levers, then every time the bandit A is pulled, so every time the lever is pulled, we're going to assume that the reward is simulated from a normal with mean Q star A, which was determined in the previous step, and variance 1. Okay, so this whole experiment is referred to as the 10-arm test bed. Why 10? It's because k is equal to 10, we use 10 levers. So just a visual representation of that problem here. So for a fixed run, let's say our first run, the first step was to simulate the expected value of all these levers. So all these Q stars here were simulated randomly, each from a normal 0, 1. And then once we've simulated these Q stars, then this gives us the reward distribution for all lever. Okay, so let's say you sample from lever 4 at some point in the run, then your reward will be normal with mean Q star 4 and standard deviation 1. So you can see here the distribution of the reward from lever 4, and this distribution is provided for all levers here. Okay, so in that case, the optimal lever or bandit would be the third one. Okay, so this we don't know in practice, we don't know the expected value, but here if we knew it, we would sample all the time from lever 3 in that run. Yeah, okay, so this figure, just a quick note, it's from the textbook. I didn't draw it myself, so I want to acknowledge that. Okay, so what we will do here, we will consider this 10-arm testbed experiment, and then we will consider 3 different strategies to pick the actions within each run. Okay, so we will consider 2 epsilon-greedy policies. Okay, the first one with epsilon being 0.1 and the second with epsilon being 0.01. Okay, so here epsilon being 0.1 means you're going to explore 10% of the time, whereas the epsilon being 0.01 means that you will randomly pick an action 1% of the time. Okay, so there will be much more exploration from the first policy than for the second one. And these 2 epsilon greedy policies will be compared to a fully greedy policy, which always selects the greedy action, which is the one which looks best as of the current information. Okay, so we're going to see in the experiments where the results are presented shortly, then the epsilon greedy policies, they provide higher expected rewards over the long run. Okay, so next we're going to present a figure which illustrates the following quantity. Okay, so we're going to have curves in these figures, and each curve, each point of of a given curve represents the average reward obtained until time t versus t. Okay, so this will be the first panel, which will represent this quantity. The second panel will represent the percentage of time that the optimal action was selected by time t versus t. Okay, so by optimal action, we mean the action with the true highest expected reward. Okay, not the greedy action, but the optimal action. Okay, optimal means the true highest expected reward. Greedy means the highest estimated expected reward. Okay, and furthermore, we said we did that for 2,000 runs, so the results presented here are average across all 2,000 runs. Okay, because averaging entails that we have a better idea of what the expectation is. Okay, so all these runs are independent, so in that sense, when we average the runs, it kind of gives us an estimate of the expected value across runs. Okay, so again, this figure is drawn from the textbook. So here we can compare. So here, this is the step t, and this is the average reward. On this axis is the average reward up until time t. Okay, so average means across all steps until time t, but it also average across the 2,000 runs. Okay, so here we can see that as you have additional plays, or as plays are being played, the epsilon-greedy strategy tends to plateau early. Okay, so the reason, and versus the epsilon-greedy ones, which reap highest expected rewards. And why is that the case? It's because here the epsilon-greedy, in many circumstances, it will miss the optimal action. Okay, so at the beginning it does very well, but on the long run, if you miss the optimal action and you never discover it, you might sample all the time from a bad action, or an action that is suboptimal, and your expected reward will plateau in that case. Conversely, if you explore, which is what's done by the blue and red epsilon-greedy approaches, so here on the long run, you can see that they provide higher expected rewards, because forcing the strategies to explore prevents them from missing the optimal action. Okay, so on the short run, they might sample more often from bad strategies, but eventually they'll have to they'll discover what the optimal action is, and they'll start sampling from that optimal action more often. Okay, so here let's look at the difference between the 10% exploration and the 1% exploration. So here, why is that the blue curve above the red curve? It's because by exploring more, you tend to discover the optimal action earlier. So this is why in an earlier stage, you obtain higher average rewards. Okay, so the red curve takes more time to discover the optimal action. However, something we don't see here is what would happen if we had more than 1,000 plays. Okay, so here the experiment stops at 1,000, but what happened if we would have 10,000 instead? What would happen is that red curve would eventually cross and outperform the blue curve. The reason for that is that it takes more time for the red curve to discover the optimal action, but once it does, it samples 99% of the time at least from it, so it stays more often with the optimal action. And for that case, once it zeroes in on the optimal action, you reap higher expected reward. Okay, so eventually, if that plot continued, the blue curve would probably continue like this, and the red curve would become higher than the blue curve. And this, we can see it in the plot below. Okay, so here, this plot gives us the average across all 2,000 runs of the frequency with which the optimal action is selected. Okay, so for the epsilon greedy approach here, we can see that there's some kind of plateau here, which means that there's a lot of cases where the optimal action is just missed, and it's missed for the rest of time. Okay, in many cases, the optimal action will never be discovered. For the epsilon greedy approach, here the 10% exploration entails exploring more at the beginning, so you discover the optimal action earlier and then you start exploiting it. So because of that, you start exploiting from your optimal action earlier, so you get a higher frequency associated with the optimal action. Okay. Exactly as we discussed before, the 1% exploration takes more time to identify the optimal action. So this is why the percentage of optimal actions grows slower through time. Okay, but again, what would happen if we had more steps? So if this number was infinity instead of 1,000, then what would happen is that this curve would converge roughly to 90%. Okay, so a bit more than 90%. Okay, why is that the case? It's because if you explore 10% of the time, you must take the greedy action at 90% of the time, plus the time where you randomly select an action and end up taking the greedy action. So for that reason, this line would converge to slightly more than 90%. This curve would converge eventually to slightly more than 99%. So for this reason, again, the red curve would cross the blue curve eventually if we had more steps. Okay, so we can see from this experiment that on the very short run, the fully approach performs slightly better. Okay, so because on the short run, you take actions which seem the best, you're likely to have higher expected rewards than somebody which explores. However, on the long run, exploring is very important because it allows you identifying the true optimal actions and then exploiting them, not right now, but in subsequent steps. Okay, so for that reason, it's very important to explore on the long run if you want to improve your expected rewards across the entire run across all plays. Okay, so here this is a small recap of what we just shown here. So having a higher epsilon, so epsilon 10% here, worked better because exploration led faster to identifying the optimal action, whereas lower exploration took more time to identify the best action. However, as we said, eventually, if M had been much larger, then the approach which explored less would eventually become better than the approach which would explore more. Okay, so we can see that at the beginning, it's very important to explore, but as time goes by and you have more certainty about your estimates, exploring becomes less important. Okay, so one lesson from that is there's no single value of epsilon which works the best from all problems. Okay, so some problems involve a lot of uncertainty and you need a lot of exploration to find a good action, whereas some other problems they entail a low amount of uncertainty, so your estimates become rapidly very accurate. So in that case, you'll need less exploration. Okay, so depending on your problem, different values of epsilon might be the best. Okay, so this is not in the slide, so I'll briefly mention it, but we said that exploring is very important at the beginning and less important eventually as your estimates become better or more accurate. So an idea you could pursue is to have what we call a schedule where epsilon, it's not kept constant through time, but it might be decreasing through time as exploration becomes less and less important. So this is what's typically done in practice, but for now we won't delve deeper into that idea. Okay, but I still wanted to let you know about this because in practice, this is what people are doing. So if you read papers about this, you might encounter this strategy. Okay, one quick detail here, the 10 arm bandit, or more generally the K arm bandit, is referred to as a stationary problem. So here what we mean by stationary, we mean that the reward distribution does not change across time for the various levers. Okay, so at play 1, play 2, play 3, play 4, etc., until play 1,000, all levers, they keep the same expected rewards and even the same distributions for their reward. However, we're going to see that in reinforcement learnings, we often face problems where the reward distribution changes through time. So, for example, if we go back to either our tic-tac-toe example from the previous chapter or the example of learning to play chess against somebody, as you play against someone, you will become better, but that person will also improve and change its strategy. So something that tended to work well at the beginning might eventually have a lesser value since your opponent kind of learned how to counter your moves. Okay, so because of that, in practice, rewards distributions associated with the various actions, they're not necessarily constant through time, but they might be slowly changing as your opponent uh, improves his strategies, or the nature of your the dynamics of your systems with which you're interacting are changing. Okay, so here in non-stationary problems, exploring is even more important. Okay, because exploring entails not only finding the values of your various actions, but it's even more important because you update your old estimates to the new continuously changing expected value. Okay, so you not only need to refine your estimate of the mean, but because the mean is changing, you need to update your values more frequently. Okay, so this we will discuss a bit more in subsequent slides. So I'll stop here for today's video, and I'll see you for the second part of this chapter shortly. Have a nice day.